Hi there, everybody. We've been talking about sequences and series in class the last week or so. We figured out how to find um, the sum of, say, the first 10 numbers in a sequence, or the first 50 numbers. We had a formula for that for arithmetic and geometric series. What if we try to add up an infinite number of numbers? Do those sums get closer and closer to something? That's kind of the question we're trying to ask and answer today. And here we've got four different infinite series here, and we want to know whether these series, as we add more and more numbers, if those sums get closer and closer to something. And there's a clue in what kind of series it is. For example, you might notice that this first series is arithmetic. We're adding 5 more at each step. So if we're adding a bigger and bigger number here each time, do you think it's getting closer and closer to something? No, it's not. This one's arithmetic. So there's no infinite sum. If we add an infinite number of numbers, or if we put an infinite number of numbers in this series, those sums won't get closer and closer to anything. So arithmetic series, there is never an infinite sum. Whether you're adding 0.1 every time, or 10 every time, or -2, doesn't matter. Arithmetic series, there is no infinite sum. We can even find D here. D is 5. That common difference, that what we're adding each time is 5. It doesn't matter as long as it's arithmetic. Those sums will not get closer and closer to anything. Let's look at this next one. This next one you might notice as geometric. This one's geometric. And the common ratio is 1/10. Right? 1/10 times 15 is 1/150th. 10th times 1/150th is 1/1500. So that common ratio is 1/10. Now, the numbers we're adding here are getting smaller and smaller. So maybe this thing does add up to something. To kind of hopefully shed some light on that, we're going to look at the formula we had for a finite sum for, say, the first 10 numbers, okay? Or the first 50 numbers, or 20, or however many you're wanting to add together. We had a formula. It was the first term minus the first term times the common ratio to the nth power over 1 minus the common ratio. Now, if we look at this, we've got 1/10 as our common ratio. And as we add more and more numbers, as we let n get bigger and bigger and bigger, we're taking this 1/10, that's our common ratio in this one, to a bigger and bigger power. That means this r to the n right here gets closer and closer to 0. Because we're multiplying more and more 1/10ths together. 1/10 squared is 1/100th. To the third is 1/1000th. To the fourth is 1/10,000th. That number is getting closer and closer to 0. So as n gets bigger and bigger, since we're multiplying it by a1, this gets closer and closer to 0. And what we're left with is, for an infinite sum, we get the first term over 1 minus r. And this is actually the formula, because this is 0. We're left with a1. We still got the 1 minus r on the bottom. That is the formula for the sum of an infinite series. Now, this does not always work for geometric series. Not all geometric series will have a sum as you add more and more numbers. They all won't. This actually only works if the absolute value of the common ratio is less than 1. Okay? So really what that means is your common ratio has to be between -1 and 1. Okay, if that is the case, then we do have, the infinite series does have a sum. And in that formula gives it to us. If the absolute value of the common ratio is greater than or equal to 1, then there is no infinite sum. So let's calculate the sum of this one. So according to our formula here, it should be the first term over 1 minus r. The first term is 1/15. Our r is 1/10. So we have 1 minus 1/10. So that's 1/15 over 9/10. Now I don't like dividing by fractions, so rather than dividing by 9/10 here, I'm going to multiply it by 10/9. We can do some canceling, 2, 3, and we get 2 over 27. And there is the sum, what this sum gets closer and closer to as you add more and more numbers to the series. Let's take a look at this one. This one, is it arithmetic or geometric? That's kind of our first decision here. This looks geometric to me. It looks like we're multiplying by a half. Half of 8 is 4, half of 4 is 2. So this is geometric. R is 1/2. Now, if the absolute value of it is bigger than 1, there's no sum. The absolute value of a half is a half. That's smaller than 1. So this one is going to have a sum again, and it's going to be the first term over 1 minus r. So our sum is going to be the first term, 8, over 1 minus the common ratio. Let's see, 1 minus a half is a half. 8 divided by a half is 16. And there is our sum. Let's take a look at this next one. 2, 4, 6, 8. Well, that's not geometric anymore. It might look like it at the beginning. You might think times 2, but times by 2 doesn't give you 6 again. So it's not geometric. This one's actually arithmetic because you're adding 2 more each time. Now, arithmetic series never have a sum. So we're not going to use the formula. The formula is only for geometric series when they have a sum. Arithmetic never have that sum, so we can stop there. These two are a little counterintuitive. You would think with adding more and more numbers that it would just keep getting bigger and bigger and bigger, but it doesn't. Sometimes it does, but a lot of times it doesn't. And try to illustrate why. I want you to think about a couple situations here. Let's say you're starting 16 feet from a wall, and each second you walk halfway there. So after 1 second, we've walked half of 16, which is 8. And then another second goes by, we walk halfway there again. So we've walked 8, and then 4 more. And then another second goes by, we walk halfway to the wall again. Now we've walked 2 more. Another second goes by, we walk halfway to the wall again. We've walked 1. What we get here, 8 plus 4 plus 2 plus 1, is the total distance walked. And it's the same series that we had here. What happens with the person is they get closer and closer to the wall, but they never make it. Because they're always just dividing the distance in half. You're only going halfway there each second. You're never going all the way. So what's that infinite sum? Well, it's 16, because that's how far you are away from the wall. Here's another way to think about it. Here we've got a square. And let's say we shade in half the square. Now the area of the whole square obviously is 16, 4 times 4. I've just shaded an area equal to 8, right? 2 times 4. Now I'm going to shade in half of the rest of it. So this is 10, this is 8. And the area of this one is 2 times 2, which is 4. And now I shade in half of what's left. And now I've shaded another 2. And again, I shade in half of what's left. And that area is 1. And the total amount that I've shaded is 8 plus 4 plus 2 plus 1 plus a half if we keep going, plus a fourth if we keep going. And we can see that that amount that I've shaded gets closer and closer and closer to the area of the whole square, which is 16. That's another way to represent an infinite sum.